video, we're going to go through the Otto cycle and look at the thermodynamic calculations going between each stage. We'll also look at what the limitations are on the Otto cycle and why we can't get higher performance by going to more extreme conditions. So here's the 4-stroke engine that we went through last time. And the 4 strokes are intake, compression, power, and exhaust. On the intake stroke, a mixture of fuel and air flows in through the intake valve. On the compression stroke, that mixture of fuel and air together is compressed till the piston gets to top dead center. The spark here to ignite the fuel and air is done by the spark plug, and that starts the power stroke as the hot gases expand and force the piston down to bottom dead center. And then the piston goes back up to the top during the exhaust stroke until it reaches top dead center. So in the Otto cycle, there's 4 stages. From 1 to 2 is isentropic compression. From 2 to 3, constant volume heat addition. 3 to 4, isentropic expansion. And 4 to 1 is constant volume heat removal. Using our equations we developed for ideal gases and constant specific heats, we can then find the temperature ratios based on the changes in volume. So for T2 divided by T1, we have V1 over V2 to the exponent of k minus 1. Note that here we have T2 on the top, and here is V1 on the top. For the constant volume heat addition, Q is equal to delta U, which is equal to CV, T3 minus T2. For the isentropic expansion, we can use our isentropic formulas again for ideal gases with constant specific heats. So then we have V3 over V4 to the exponent k minus 1. The constant volume heat removal, again doing a control mass, we have delta U equals to Q, or CV is equal to T1 minus T4. Now, if we have variable specific heats, then we have to use our air tables that are in table A17 of the textbook. We have these properties VR, they're functions of temperature. Similar to when we were going through gas turbines and we had PR, and the PR was a function of T. This is the same thing, but we're looking at volumes instead of pressure. So from 1 to 2, the ratio of volume change is equal to the ratio of changes in VR. Same with isentropic expansion. Now, the engine performance is limited by what's called the compression ratio. As we mentioned previously, that's equal to the maximum volume over the maximum or minimum volume in the cylinder. Or in other words, that is V1 over V2. Now, the higher the compression ratio, the higher the performance. However, we can only go so high with the compression ratio, otherwise we'll get what's called engine knock occurring. For a spark ignition engine, typically it's only around compression ratios of 10. Now, what is engine knock, you might ask? Engine knock, also known as detonation, also known as pinging, is auto-ignition of the fuel and air. When the piston here moves up to top dead center, the temperature goes up as the compression goes up. So as the temperature's high, then that could cause the fuel and air, which are already in the cylinder, to auto-ignite. We want the ignition to occur at the time we specify, which is when the spark plug goes off. When the spark plug emits a spark, we start to get a flame. This flame starts around the spark plug and goes out throughout the cylinder. Now this occurs over a finite time, and the combustion creates more heat. So the mixture of fuel and air is heating up as combustion goes on. With the addition of more heat, we can get some of the fuel getting hot enough that it starts to ignite on its own. So we get what's called multiple ignitions. So here we have auto-ignition. And this is called engine knock because it makes a pinging noise or a knocking noise, or it's detonation of the fuel when we don't want it to occur. Now this can be damaging to the engine, as shown in the diagram here. This here is a piston. And you can see the damage here on the piston. And that damage is due to engine knocking. So in summary, if we go back to this diagram here, this auto-ignition is bad. We don't want that to occur because it decreases the performance of the engine, but it can also lead to damage of the engine. So in summary, in this video, we went through the Otto cycle. We looked at the calculations going through each stage using variable specific heats and using constant specific heats. We determined that the engine's limited by the compression ratio because the compression ratio can only be so high or else engine knock will occur, which can cause damage to the piston or to the cylinder or to the valves, as we saw in the picture.